The purpose of this video is to demonstrate kind of the nuts and bolts of a regression. Oftentimes we can use programs such as Stata, SPS, SAS, R, and even Excel to run a regression or calculate a regression. What I want to show here is the kind of the nuts and bolts, the why or the how of a regression by using the equations using equations to calculate each of the different items that you would see in a regression output, such as the p-value, the t-stat, the r-square, the intercept, the standard errors, all those things. We're going to use different equations, just using x's and y's, dependent variables and independent variables, to calculate these, rather than using functions or just plugging the information into a statistical program. The question we're going to look at answering today is the number of pairs of socks that a shoe store should order based on its history and expectations of the future of shoes being sold. So let's say the shoe store does a great job of ordering the right numbers and the right types of shoes, but tends to either overstock or understock socks. And they want to get a better job or do a better job of predicting the number of socks being sold. So we have 30 days worth of sales information for this company. Each day shows the number of pairs of socks sold and the number of pairs of shoes sold. So I've also got, so the name of this workbook is Regression Example. And then I've also got a document here called Regression Equations. And I'd just like to run through a few of these definitions to start off with. In a regression, we usually have a left-hand side variable, and that's the y variable. That's the dependent variable. That's the variable we're trying to explain. We're trying to explain the number of socks being sold by using an independent variable, x. In our case, that's the number of shoes sold. So we're looking to see if there's a relationship here, and if we can use the number of shoes sold to predict the number of pairs of socks that will be sold. N is the number of observations. So in our case, we have a month or 30 days worth of observations. Yi, and you'll see Yi and Xi a lot. So Yi is equal to the ith observation of the dependent variable. So if I said I is equal to 7, so Yi would be equal to 68, and Xi would be equal to 106. And we'll start off by calculating the regression coefficient. Now, I'm not a statistician, so some people might like to see a small b here, or b hat, or small b hat. But I use the Greek symbol beta, for the capital letter beta, for the regression coefficient. And that's equal to the covariance of x and y divided by the variance of x. So in our case, that's the covariance of shoes and socks, divided by the variance of the number of shoes sold. To calculate the covariance, I'm going to scroll down here. The covariance of xy is equal to the expected value of x multiplied by y minus the expected value of x multiplied by the expected value of y. And for our calculations, this is equal to 1 divided by n, number of observations, multiplied by the sum of each of the products of x and y for each observation, minus the average number of x, or the average number of shoes sold, multiplied by the average number of y sold. So the information I want to start off with is the number of observations, the mean number of shoes, the mean number of socks. So to make things a little bit easier, I'm going to name my column for the number of socks sold. So I'm going to put my cursor in C3, press Control Shift and then down. And up here is the name box. I'm going to name this array socks. I'm going to go over to the next one, D3, press Control Shift and down. And I'll name this array shoes. So now I don't have to highlight this column every time I want to use those numbers. So over here in L2, I'm going to put in daily average of socks. And daily average of shoes. And we also want to put in the number of observations. So this is n. And we know the number of observations is 30. So I'm going to name this cell obs, because we don't want to name it n because it'll actually reference the column n. So I'll name this column obs, and name the cell obs, and then my daily average of socks is equal to 1 divided by obs multiplied by the sum of socks, and then the daily average number of shoes is equal to 1 divided by obs multiplied by the sum of shoes. Okay. So we get 61.3 pairs of socks sold each day and 93.57 pairs of shoes sold each day on average. Next, I want to calculate the product of socks and shoes for each day. And this is going to be equal to socks multiplied by shoes for each day. Notice I didn't put in socks and shoes, I just highlighted C3 and D3. I'm going to pull that down all the way. And so my covariance of shoes and socks is equal to 1 divided by obs multiplied by the sum of these products minus the daily average number of socks multiplied by the daily average number of shoes. I'm actually going to be using these numbers quite a bit, so I'm going to go ahead and name these. The daily average number of socks is equal to I'll name that Y mean, and the daily average number of shoes, I'll name that X mean. You can see if I highlight these, then it says X mean and Y mean. So my covariance of shoes and socks is 64.2633. Now I want to calculate my variance of shoes, and the variance of shoes will be our denominator in the regression coefficient, so I'm going to open that up. So the variance of shoes is equal to 1 divided by n multiplied by the sum of xi minus x mean squared. So I'm going to create a column of xy minus x mean squared, xi minus x mean squared. So this is equal to the number of shoes, open parentheses, the number of shoes minus x mean, which we've already named, squared. So I'll highlight these and pull it down. So the variance of shoes is equal to 1 divided by obs multiplied by the sum of xi minus x mean squared. So our regression coefficient, or beta, is equal to the covariance of shoes and socks divided by the variance of shoes, or 0.59. Our intercept, and that's also known as the alpha, so I'll put it here, intercept, and I'll put in here by beta, slope. So if I go back out to my document, I can see that the intercept is equal to 1 over n multiplied by the sum of yi minus the beta multiplied by xi. So now I want to create a column of yi minus bxi to get the intercepts, or to get the intercept. So I'm going to name my beta here, beta. So my column here will be yi minus beta times xi. And that's what I'll put in here, equals the number of socks minus beta multiplied by the number of shoes. So I'm going to pull that down all the way. And then my equation says I want to take 1 over n multiplied by the sum of those, or the average number of those, equals 1 divided by obs multiplied by the sum of and I get 6.091. So this is my intercept, also referred to generally as alpha. So I'm going to name this alpha. I don't name it intercept, although that may be okay to do. That's also a function in Excel. For the same reason I don't refer to this as the slope, that's a function in Excel. We'll see that possibly later. So we've calculated the alpha, the intercept, and the regression. So that's the intercept in the beta or the regression coefficient that you might see, or that you will see in regression outputs. So now we want to get into the R-square. I have here the variance of the dependent variable, the total sum of squares, and at this point I'm not going to calculate the variance of the dependent variable, but I did want to include this so you could see the relationship between, if we just calculated the variance of socks and the total sum of squares, they look very familiar. The difference between the variance of the dependent variable and the total sum of squares is that we don't take the divided by n. We just multiply yi minus y mean squared and find the sum of that. So I'm going to start with that. I'm going to name the column here yi minus y mean squared and then I'm going to pull that down all the way. So my total sum of squares, the reason why you'll see it as SST is just to be consistent with SSR and SSE, which we'll calculate too. But it could be sum of squares of total or something like that. But the idea is that this is the total of the differences between each observation for socks and the mean for socks. And we square it so that it's always positive. So SST is equal to the sum of yi minus y mean squared, or 1350.3. So that's our SST. So we've calculated the total sum of squares, which is 1350.3. The next thing we want to calculate is the SSR, or the sum of squares of the regression. And the calculation for that is the sum of the predicted y in each case, which is yi hat, minus the mean y, or the average y, squared. The first thing we need to do is calculate the predicted y for each observation. I have that up here as yi hat is equal to the intercept plus the beta multiplied by xi for each observation. So we calculate y hat is equal to alpha plus beta multiplied by my x, shoes. Pull that down all the way. And now I want to calculate y hat minus y mean squared. Pull that down all the way. And so my SSR, again, is going to be equal to the sum of y hat for each observation minus the y mean squared. And that's 1137.55. And then we can also calculate the SSE, the sum of the squared errors, which is calculated as yi minus y hat squared, and there actually should be an I here. Put that one in. And yi minus the predicted level of y for each observation is equal to the error terms, the sum of the error terms squared. So we need those error terms later on. Actually, yeah. So I'm just going to calculate the error. So it's going to be equal to the number of socks actually sold during that day minus y hat and then I'm going to put in here equal the error squared. So it's going to be equal to K3 in this case, squared. And I'll pull that down all the way. So this is going to be equal to the sum of the squared errors and what you should see here, and we'll double check this, is that SSR is equal to SS plus SSE is equal to SST. So I'll just double check that. And I do get the correct answer. SSR plus SSE is equal to SST. Our R squared then can be calculated in two ways. Give us the same answer. R squared is equal to SSR divided by SST, or it's equal to 1 minus SSE divided by SST. Give us the same answer. So here I'm going to put equals SSR divided by SST, and I get an R squared of 0.842. So what that means is that the variance or the variability of X, in this case is our shoes, explains 84.24% of the variability in the socks. So it does a pretty decent job. So we probably could use this to predict the number of socks we could order. So the next item I want to calculate, so we've calculated the R square, we've calculated the intercept, the regression coefficient. Now I want to calculate the standard error of the slope and the standard error of the intercept. And from that we can determine if the slope and the intercept are statistically significant. So these are a little bit more challenging equations. So for that reason, I'm actually going to leave open my document so we can look at that as we go through the calculations here. So the standard error of my slope is equal to the sum of the squared errors, which we've already got that, divided by n minus 2, divided by the sum of xi minus x mean, which we already have, and we take the square root of that. So standard error of the slope is equal to the square root the sum of the squared errors. Oops, I don't even actually have to put that. Sum of my squared errors. And I want to divide that by the number of observations, n, so we put obs, minus 2. And then I want to divide that by the sum of xi minus x squared. Minus x mean squared, sorry. Xi minus x mean squared. I have that. I want to put a closed parentheses there. And I get a standard error of the slope of what would be 0.048. So now we're going to calculate the standard error of the intercept. And the calculation for that is fairly complicated. So I'm going to leave my document over here open. The first thing we need to do is recognize the variables that we have. This numerator in the first argument is actually the sum of the squared errors, which we've already calculated. We've got the number of observations. We don't have xi squared, or the sum of xi squared, as a variable yet. So I'm going to create that. Xi squared is equal to the number of shoes squared. So I have that d3 up caret 2 for xi squared. So now I've got the column for xi squared. Now I can calculate the standard error of my intercept. I start with equals square root the sum of the squared errors divided by, open parentheses, observations minus 2, then close parentheses, so we get all of that in our square root, multiplied by the sum of, or excuse me, the square root of the sum of, actually here I want to put 2 parentheses, so the first parentheses is to capture everything we're doing within that square root. The second one is to define the numerator. So I'm going to take the sum of all my xi squared, and I'll put a closed parentheses there, and then a second closed parentheses, so that's the numerator. And then I'm going to divide that by my denominator, open parentheses, the number of observations multiplied by the sum of xi minus x mean squared. And we've already calculated xi minus x mean squared. So I'll go over here to that column, xi minus x mean squared, and highlight that. And then close parentheses. And then a third close parentheses to say that's everything for our equation, and we get 4.554,005. So our standard error of the slope would be actually 0.048, and our standard error of the intercept is 4.54. Down below we have the t-statistic. So this is the test statistic for a student's t-distribution. And that's equal to the slope. This is for the slope. So the t-stat for the slope is equal to beta divided by the standard error. And then the t-stat for the intercept is equal to our intercept, our alpha, divided by our standard error of the intercept. So we get 1.34 there. So now the last thing we want to do is calculate our p-values. These are the probabilities of our slope occurring and our intercept occurring by random chance. The next thing we want to do is calculate the p-value for the slope. And this is going to be equal to, we're going to cheat a little bit here. We are going to use an Excel function. What we would normally do in this case is look up a value on a table, so we're not really doing a calculation we wouldn't otherwise do. So our p-value here is equal to t-dist. Our x is actually equal to our t-stat. So our t-stat is 12. Our degrees of freedom are the number of observations minus 2. And our tails, we're looking at a two-tailed distribution. And so we get a very, very tiny number. Our p-value for the slope is 0.00000, very small. Our p-value for the intercept is equal again to t-dist. Our x is our t-statistic for the intercept, comma, the number of observations minus 2 for our degrees of freedom, and then a two-tailed distribution, and we get 0.1904. So there is a very, very tiny chance, and certainly less than a 5% chance, which is normally what we would look at here. Is there more than a 5% chance that this is happening from random chance? Certainly not in this case. It's effectively a 0% chance that our slope is occurring out of random chance, that there is in fact a statistically significant relationship between the number of shoes sold and the number of socks sold. However, the intercept is not statistically significant at the 5% level. So now that we've calculated all of the output that we want to get from our regression, now I'm going to double check that by using data analysis in Excel. And you can get a data analysis by going to File and Options, and go to Add-ins, and go to Excel Add-ins, down here Go, and you'll want to check the Analysis Tool Pack. So if this data analysis isn't up there, you'll want to go through that to get it. Now I'm going to go to Data Analysis. I'm going to select, and you see here there's a lot of different options here for data analysis. I'm going to select Regression, go press OK. I'm going to select Labels, and because I selected Labels, I'll highlight the labels for each of my variables too. So my Y variable is going to be socks, and again I selected the label socks. And my X range, my X variable, is going to be shoes. And we don't want our constant to be 0. Our constant is our intercept, so we have an intercept calculated by that. I'm going to put it in a new worksheet. And then I'm going to also include the line fit plots. So I have my answers here. So what we see is that when we compare our outcomes, our R-square here is 0.84244. Go over to our original sheet. Our R-square is 0.84244, so that's right. Our intercept is 6.091266. Our intercept is 609.1266. Looks good. Our beta is 0.59. Our coefficient for shoes is 0.59. Here you can see the regression sum of squares, the residual sum of squares, the total sum of squares. Double check that, you're going to get the same numbers. Our standard errors are the same between the two. Our t-stats are the same between the two. You get that 12.236, 12.236. Our p-values are the same. And so our outcomes, as you can see, we just use our different formulas for each calculation, so you can see how we're plotting that line, we're predicting those outcomes. This is actually our line fit plot. So the red observations are the predicted level of socks for the level of shoes, and the blue observations actually reflect the total outcome of the actual observation. You can see it's a pretty tight fit, so it has high explanatory value, high R-squared there. So that's the end of this example. I hope it was useful for you.